And here's the initial intuition. The neuron, which is a cell in our body, looks like this, where there's a lot of dendrites here. This ties up with other neurons that look like this, and then send signals, and each signal travels into this little tentacle-like structures, and so the neurons network each other. Now each of these things have a different strength, and each of these dendrites actually activates with a different strength. The intuition is the same in computer science. Basically, we'll try to create a neuron that we will later call a perceptron. A neuron, a cell that has many inputs, and each input, x1 and then x1 to xn, has a different intensity or weight, which is weight I0, weight I1, weight I2, weight IN. Once this activation happens, there's some output that goes through some function and produces the final decision that the neuron triggers. So now just a few numbers here. Consider the humans. The neuron switching time is approximately 1 millisecond. The number of neurons, the most literature says is about 10 to the 11th or 10 to the 10th. Connections per neuron, 10 to the 5th or 10 to the 4th. Now, a human recognizes a scene in 0.1 second. There is a lot of parallel computation going on, okay? This is in humans. Now, artificial neural networks. There are many neuron-like threshold switching units, which are the structures that I showed you in the slide before. There are many weighted interconnections among units, which I also explained before. It's highly parallel distributed process, and its emphasis on tuning weights automatically. So the idea is that these weights that determine which signals are more important will adjust automatically depending on what the goal of the output is. Now, when to consider a neural network? What are neural networks good for? Usually when the input is highly dimensional, discrete or real valued. So for example, sensors, many sensors, or the sensors have, take for example 1 second of sensory data, and they produce a number every 2 hundredths of a second. That's a lot of numbers in 10 seconds. That's a highly dimensional value. When the output is discrete or real valued, again, it's similar. When the output is a vector of values, now it's not just a lot of values coming in for, say, 10 seconds, but it's a vector of values. So, for example, we will get weather data, and there are multiple sensors, and at the exact same time, you have about 100 different values from 100 different sensors: humidity, air pressure, time, what season it is, certain conditions of the sky, temperature. There are many data. For one data point, there are many data being captured. That would be a vector of values. Also, they're good when there's noisy data, because when a neural network is trained, it's quite robust when against noisy data. So data that's really false positives or false negatives. Now, when you do not know what that function that produces the correct output is, so for example, it's not a tree, you don't know if it's a tree, you don't know if it's a linear function, you don't know what kind of function can produce the output. It's good for learning functions. And lastly, when the human readability of the result is unimportant, so you don't really want to know exactly what the function is or what the result means in terms of, the tree, for example, the decisions that went on. You can detect one leads to the other and so on and so forth. In neural networks, this is quite less tractable. And here are some examples. Speech recognition, image classification, financial prediction, so markets and whatnot, handwriting recognition, and optical character recognition. And there's actually, there was in the late 90s or mid to late 90s, a self-driving car that had a lot of sensors, and that's the way it drove itself, right? Using a lot of sensors, and that sensor input was a vector that was being outputted to a neural network that would decide whether or not to turn, continue, and so on and so forth. Let's talk about uh, uh, let's talk about the perceptron. That's what's going to come up next.